Good morning, students. Today we are just continue with the unit 3 and our topic is today the periodic trend in the physical properties. Now the properties which will be considered here will be the atomic volume, ionization enthalpy, atomic size, electron gain enthalpy and the electronegativity. Now these properties really are related with the electronic configuration and the variation in these properties show a regular trend across the period and down the group. And what is the significance of going through these physical properties is that they affect the physical properties of the elements like melting point, boiling point. So we are going to study these periodic properties one by one. So first we will discuss the atomic volume. Now students, what is the atomic volume? It is the volume occupied by 1 mole atoms of an element at its melting point in the solid state. Now the atomic volume will be related definitely with the atomic mass, and it helps to just get the relation between the atomic mass and the density, or if we know these values atomic mass and density, gram atomic mass and density of that element, we can find out the atomic volume. So students, here the atomic volume, what is the atomic volume? It is the volume occupied by 1 mole of or 1 mole atom of an element at its melting point in solid state. Or we can express it in this way, that atomic volume is equal to gram atomic mass of that element divided by density of that element. Right? Now, the next is, which we will discuss here, is the variation, how it is going to vary across the period and down the group. Now students, in the variation, we will discuss in two heads. One is across the period. Now students, when we move across the period, the atomic volume is going to decrease, right? So on moving across the period, it decreases, reaches a minimum value, and then increases. So students, if it is so, then whose atomic volume is going to be maximum? It will be of the alkali metal in a respective period. Now students, second is down the group. So students, on moving down the group, the atomic volume is going to increase. So on moving down the group, down the group, it increases. Right students? So this is about the atomic volume. Now when we move across the period, it will first decreases, it will then decreases, reaches a minimum value, and then it start increasing. Now on moving down the group, there is increase in the atomic volume on moving down the group. Now students, we will discuss the next periodic property or the physical property, that is the atomic size, right? So the atomic size, generally it is referring here the size of the atom, right? So what are we going to interpret by the size of the atom here? That the for that the atom is to be considered to be a sphere. Now if it is a sphere, we will have the radius of it, right? So atomic size, it is the distance, right, from the center or of the nucleus to the outermost shell, or we can say that it is a radius of the atom, right, which is considered to be the sphere. But if we just go through the wave mechanical model, here they have told that the atom cannot have a rigid boundary, right? So if we just see that probability boundary diagram also, so there is no rigid boundary or well-defined boundary of an atom. So in that case, we can't just find out the radius of an atom, right, from the center of the nucleus to the outermost, because there it is not possible that that the possibility of an electron, right, from right away from the nucleus will be zero. We can't say that the probability of getting an electron just a long distance or at a large distance from the nucleus will be zero. So that means that it doesn't have a well-defined boundary. Second is, an atom cannot be isolated, right? We can't isolate a single atom, and the atom is too small to just take a scale and just measure the radius of an atom, right? And next is that the atom is the probability distribution of an electron in of an atom depends upon the surrounding of an atom also, that which kind of surrounding it is having, that means that which kind of other element it is present around it, and also depend upon the bonding state. So from these we can conclude that the just by having the radius of an atom, right, from the center of the nucleus will not be sufficient, right? So we have, so the size of an atom will be expressed depending upon the surrounding or the bonded state of the atom. Now here we means that if the atom is holding another atom or is linked with the other atom through the covalent bond, we will say it to be a covalent radius, right? If it is forming an ionic bond with its surrounding atom, right, it will be known as the ionic radius. Now, if it is a metal and it is in its crystal lattice or surrounded by its like atom, like it will be forming the metallic radius, right? And we have the van der Waals radius also. So that means the atomic size is now going to be expressed in covalent radius, in the form of ionic radius, in the form of metallic radius or the crystal radius, or in the form of the van der Waals radius. So the second uh, physical property, or we can say that the periodic property here is now the atomic size, right? So just as I said that due to the restrictions, we are now not only going to say the atomic size is just the distance of the, or just the radius of an atom will be known as the atomic size or atomic radius. Now the atomic size is going to be expressed, atomic size, right, it will be expressed in terms of the atomic radius, and that will be a covalent radius, which can be a van der Waals radius, It can be a metallic or a crystal radius, or it can be an ionic radius. Now this division of the atomic radius, whether it is polymer, covalent, van der Waals, metallic and ionic, will depend upon the nature of bonding which that atom is having with its surrounding atom. Right? So we will just continue ahead. So we will start with the covalent radius. Now students, what is a covalent radius? So the first one which we will discuss here is the covalent radius. It is half of the internuclear distance between the two covalently bonded atoms, right, in the solid state. So between the two covalently bonded atoms in the solid state. Now students, here the two covalently bonded atoms can be either homoatomic or they can be heteroatomic, right? So let us take here first the example of homoatomic here. So let it be, this is there, we have got two atoms. Now let it be A and A, that means they are homoatomic. Then the internuclear distance, that is this one. We will just get the half of it done. So this will be the, or either this will be the, right, the covalent radius. Now if we have the heteroatomic molecule, in that case, right, let it be A and B, this is A and this is B. So we are going to take the distance from the nucleus to that of the, this will be the mean position of the shared pair electron. So here also this distance will be the covalent radius of A atom, and here this is going to be the covalent radius of B atom, right? In that case we are just taking, again it is a half of the internuclear distance, but here we are just going to count the distance of this atom from its nucleus to the mean position of the shared pair electron. The shared pair electron that is covalently bonded, with shared pair of electron will be there. So we'll just take the mean of this distance of the shared pair of electron and the center of the, or center of the nucleus, right? So this distance will be known as the covalent radius. Now the covalent radius, right, is we can say the smaller here. Why? Because it is formed by the overlapping of the atomic orbitals, students. So just go through it properly, have a look on it, that the covalent radius, if it is a homoatomic molecule, that time there is just, we are taking the half of the internuclear distance, and if it is a heteroatomic molecule, in that case we will take the distance between the nucleus of the atom and the mean position of the shared pair of electrons, right? Again I'm repeating, if it is a heteroatomic molecule, in that case that will be the distance between the nucleus of the atom and the mean position of the shared pair of electrons.